Now you can keep going past kilo. So for example, 10 to the 6th is called mega, 10 to the 9th is called giga, and 10 to the 12th is called tera. And you could also get smaller and smaller. We talked about milli. Micro would be 1/1,000,000th of something, 10 to the -6th. Nano would be 1/1,000,000,000th. And pico would be 1/1,000,000,000, 10 to the -12th. And you probably heard use these in terms of milligram, kilogram, and gigahertz. Gigahertz. What does that mean? The speed of your computer is 5 gigahertz, written this way, Hz. Well, that means 5 times 10 to the 9th hertz. Something is oscillating that fast. Usually that's involved with computers. All right, so this next few slides I'm going to skip, and I want to go into using units in science. All right, this is where we just finished off. A liter, sometimes called a cubic decimeter, because it's 1 decimeter or 10 centimeters on each side. But using units, so when we measure things, we use units, but we use equations, we multiply those units. So, for example, if you multiply 5 centimeters times 2 centimeters, what would you get? Well, 5 times 2 is 10. You get 10 square centimeters. So you're multiplying two numbers that are length, but the product of them is not length anymore, it's area, because this is 10 square centimeters right over here. How about if you take 10 cubic centimeters divided by 5 cubic centimeters? Well, 10 divided by 5 is 2. Yeah, that's pretty easy. But centimeters, this is centimeters. I think I have it over here. This is centimeters times centimeters times centimeters. One of these centimeters cancels one of these. So the answer is 10 divided by 5 is 2. And now, since these have canceled, 2 square centimeters. All right, I know this is easy, but let's see how you do in this one. So we have a basket here. We have a number of pairs. Here's the pairs. I'm sorry, this is the pairs. This is the oranges, and these are the pairs over here. So if I ask you to, can you take the number of pears divided by the number of oranges, what do you get? Well, pears is 10, yeah, we know that. Oranges is 2, and 2 pears divided by 10 pears divided by 2 oranges. Let me just check here. I'm just seeing you vote. So what do you get? You get 5 what? Pears per orange. Actually, this is not 10. I'm sorry, right? It's probably was clicking at me, right? That I messed this up. This is 6 pears divided by 2 oranges. All right, and you get 6 pears divided is what? It's 3. What? 3 pears per orange. That means the ratio of pears to oranges is 3 to 1. For every orange, there are 3 pairs. So here's 3 pairs for this orange, and here's 3 pairs for this orange. 3 pairs per orange. You could write it in words this way, but usually you write it that way. Of course, that comes very often in physics. You take 10 meters and divide it by 2 seconds, you get 5 meters per second. 5 meters per second. If you take, let's do a conversion. How much is 12 inches divided by 1 foot? Well, 12 inches per foot. Okay, read this with 12 inches per foot. And we know that 12 inches is the same as 1 foot. So this actually is a fraction that's equal to 1. We're going to keep that in mind for the next part. Dimensional analysis means that if you use in equations, if you use numbers that have units associated with it, then the answer, say this is the equation you use, A is equal to that, T is equal to that. What is D? D is equal to that. And this is one of those questions where you can pose it as a question. Which one of these answers? Let's talk this a minute. I'm not going to keep yapping on. I'm going to pause right here a little bit. Which do you think is the right answer? Well, so you have AT squared. So A times this squared, that's 10 meters per second squared, times this squared, which is 10 seconds squared. Because you square seconds, you get seconds squared. So the seconds cancel off. This is squared, DAT squared. So what you get is 10 times 10 is 100, but 100 meters. 100 meters is this answer here. Okay. And of course, this is an equation we'll be coming across. D stands for distance, and of course, distance is measured in meters. So it should come out to be not seconds, not meters per second, but it should come out to be meters. Supposing you purchased 10 gallons of gas and you paid $30. And I have a question for you. Number one. So 10 gallons equals $30. This is what's called a conversion factor between gallons and dollars. How many dollars do you pay for a gallon? Well, dollars per gallon. So you're going to take dollars. Well, the next thing I'm going to ask is how many gallons can you get for a dollar? So the first one is you're going to take gallons per dollar. So you're going to take 30 gallons per dollar. So you're going to take 10 gallons and divide it by gal. So right with a mouse and divide it by $30. And you get 3.3 or $3.33 gallons per dollar. So for a dollar, you would be able to buy 3.3 gallons. How many gallons for a dollar? So that's this answer to this question. How many dollars do you pay for a gallon? Well, you do it the other way around. $3 divided by 10 gallons gives you 0.3 dollars per gallon. Okay, so that's the way units work in science.
Professor?
Yeah.
I have a question. The previous problem we just did, why is it not 1,000 squared? I don't know, I just want to make sure.
Maybe it is. Maybe I made a mistake. T squared, yeah, it is 1,000. You're right. Thank you very much. T squared, I squared T and I got 100. I got 10 and I squared the seconds, but I didn't square, this is not 10. 10 squared is 10 squared. 10 squared is 100. 100 times 10, yeah. So this is not the right answer. Thank you for pointing that out to me. And if I do this occasionally, I get carried away, and remind me, if you see a mistake, remind me. Okay, let's see, what am I up to? Okay, so we just did this. So we did 10 gallons per dollar. So this would be 0.33 gallons per dollar. If you do it this way, $30 per gallon, there would be dollars per gallon. So the Earth rotates on its axis once 24 hours. So we know that how many degrees does it turn every hour? 360 degrees equals 24 hours. So how many hours per degree? Well, again, 360 degrees divided by 24 hours turns out to be what? Well, this divided by that is 15 degrees per hour. So that's the answer to the first question. How many hours per degree? You do it the other way around, right? You took 24 up here, 360 down here. You get, that's going to be a small number, right? Here it is, 0.067 hours per degree. Don't forget, I did remember to record this, not from the very beginning, but pretty good. Most of the important stuff I got recorded. Let's do something easy. You want to convert $25 to quarters. I mean, you probably can know how to do this if every quarter is $4, but let's say let's do it the way we've been doing things. So we need a conversion factor to convert. To convert from one unit to another, we need, how are they related? Oh, there it is. $1 is 4 quarters. We know that. So we can multiply $1 like this, or we can do it the other way around. In this case, this would be 4 quarters per dollar. In this case, it would be $0.25 per quarter. We want to convert dollars to quarter, so that's how you would do it. So dollars per quarter. But keep in mind that these are all one. Yeah, the units come out to 0.24, but basically the denominator and unit, and if you use the conversion factor, numerator and denominator are the same, and any fraction which has the same numerator and denominator is 1. So basically the way you're doing it, you're saying $25, and I'm going to multiply it either by this or that. So if I want the dollars to cancel, I multiply by that. I'm sorry, no. If I want the dollars to cancel, I multiply it by that. Right, so $25 multiplied by 4 quarters per dollar gives you
6.5.
24, yeah, gives you 100.
Mm-hmm.
Now, if we do it the other way around, okay, if we do it the other way around, well, basically this is the problem, so we don't have to do it the other way around. But we'll do just similar problems. Conversion factor between inches and feet is 12 inches equals 1 foot. That means this is equal to 1, and this is equal to 1, since numerator and denominator are the same. So let's say 6 inches is how many feet? Now we know, we can do this in our heads. We know it's a half a foot. But let's say you didn't know that. So you take 6 inches and multiply by either this or this, such that the units you don't want inches, are going to be on the bottom, so they will cancel off. And you will get 6 times 1 divided by 12, which is 1/2 a foot. So 6 inches is a half a foot, as we knew before. So for example, I'm not too big. I'm 5.5 feet tall, 5.5 feet tall. How many inches is that? So I'm going to put it, this is my height. I'm going to multiply by a fraction, which is 1, basically, formed from this, the relationship between inches and feet. And I'm going to try to get the feet to cancel out. So where do I put the feet? On the bottom. Where do I put the inches? On the top. So basically the answer to that is 5.5 times 12. That's 66 inches. Now, supposing I still have this, how many centimeters would that be? Well, you know 66 inches. you got to know the conversion factor between centimeters and inches. And here it is. 2.54 centimeters equals 1 inch. So basically, I'm starting off at 66 inches. And where am I going to put the inches? Things I don't want.
At the bottom. That's
right. You're going to put them on the bottom because it's going to cancel. Then therefore, you're going to put this on top. Don't forget, you're multiplying by this fraction, which is really 1, because numerator and denominator are the same. And therefore, you get 2.54 times 66. It equals 167.6 inches. Centimeters, sorry. 167.2 centimeters. So this is 200 inches. I'm not going to do that. It's a different number. But let's say we want to convert something where we don't know the conversion factor, but we can get to it. We want to convert 1 week to hours. Now, I don't know what the conversion factor is between week and hours, but I know this, that 7 days is 1 week, 24 hours is a day. So I'm going to start with 1 week. And I'm going to use these two conversions so that things we don't want will cancel. So 7 days per week, I'm going to put the week on the bottom, the 7 on top. 7 days per week, the weeks will cancel. And then 24 hours per day, well, we can see that the days will cancel. So weeks cancel here, days cancel here, and therefore 7 times 24 is 168 hours is left. It didn't cancel. Okay, so this is called a double conversion. Here's another one. 1 year to seconds. So, for example, you want to know in 10 years is how many seconds, or 5 years is how many seconds. Well, let's see if we can figure out 1 year is how many seconds. Again, you're going to multiply by a bunch of conversions, but you know how many seconds per minute, minutes per hour, hours per day, and days per year. You know that. So you notice that this will cancel that, this will cancel that, this will cancel that. And so what's left? If I multiply all these numbers, what's left? On top, you'll have some number of seconds, and in the bottom, you'll have 1 year. Multiply 60 by 60 by 24 by 365, and you get 3.15 times 10 to the 7 seconds per year. So we just did that. This is just another slide. It tells you more or less what I just did. You can have it on the video. And then you can do the same thing. How many seconds is the age of the universe? If the age of the universe turns out to be 33.8 times 10 to the 9 years, we're not going to do it here. Well, I'm going to show you the answer. But you would do it the same way. And I believe by using this, seconds per year, you can multiply this by that, and you get how many seconds in a year, since the year will cancel off. Okay, the year will cancel off, and this is just 1, so that's the answer. This is something that's going to be familiar. Let's say you're measuring kilometers per hour, the speed of something kilometers per hour, but you want to change it to meters per second. So again, this is a multiple conversion. First of all, you got to change the 100 kilometers to meters. Well, that's easy. We move the decimal, or you can multiply by 1,000. That means because there are 1,000 meters per kilometer. And then this is in hours. You want to change the hours to seconds. You're going to multiply 1 minute and 60 seconds. Well, 1 hour and 60 minutes, then 1 minute and 60 seconds. And you can see all the units you don't want will cancel. And you end up with meters per second. Meters per second. So there's also a possibility of, for example, your car is going miles per hour, 60 miles an hour. How many meters per second is that? We're not going to do that. We're going to save that for a little bit later time. Well, this is it right here. 60 miles per hour is how many feet per second? Okay, so here are the multiplications that you're going to do. And I'll leave it up to you to figure out what the answer is over here. A little bit of algebra. We're going to review if A is equal to B divided by C, then B is equal to what? Well, you know that in algebra, whatever you do to one side, you have to do to the other side. So if you want to solve for B, you got to multiply both sides by C. So the C's cancel. So the C cancels here, and you get B is equal to AC. AC, which is right over here. Let's do one a little bit harder. That's too easy, I know. How about this one? Solve for C. Well, the hint is that use what you already did in the previous one, which means what did we do in the previous one? We solved for B equals C times A. So B equals C times A, what is C? Well, divide both sides by A now. A, C equals B. Divide this by A, and divide this by A. Okay, we're almost done with this. Equations in the form ax squared equals b. Solve for, what do we solve for here? Let me take a look. Of that form. So usually we'll have equations that will look like this. 5t squared equals 125. What's t? Well, again, you have to isolate the t. So divide both sides by 5. Let me go back here. Divide both sides by 5, so you get t squared equals 25. That doesn't solve for t yet. What do you have to do here? You have to take the square root of both sides, the square root of this and the square root of that. So the square root of t squared is just t, and the square root of 25 is 5. So that's how if you handle a square in an equation. But how about if you find yourself in an equation that is of this form, and you want to solve for something that's under the square root? Well, let's see if you guys can do it. Take a minute or two. So you want to solve for t? How do you get rid of the square root? You got to square both sides. So you're going to get x squared. You square the left side, and you get 5t, not 5t squared, 5t. Now you can solve for t by dividing both sides by 5. And of course, the answer is this. I'll just mention this now. We're going to come across this in a couple of weeks. The quadratic formula. You probably heard of it. Maybe you forgot how to use it. Well, it's going to come up. So say if you have an equation of this form, some number, and it could be 5 or 2 or whatever, plus some other number, times x, minus some other number equals some other number, in this case 0. All right. What's x? 5 times x squared plus 3 times x minus 2 times c equals 0. What's x? Well, this looks like a tough problem, but there's something called the quadratic formula, which tells you what x is. It tells you that x is minus b, minus this number here. That's minus b. Plus or minus, in other words, there's going to be two answers here. The square root of b squared minus 4ac. So it would be 3 squared minus 4 times 5 times minus 2 divided by 2a. And I have all the setup over here. Except I'm not doing it for those numbers. I just made those up. The numbers are like this. So this is 1, this is 2, and this is minus 3. A is 1, B is 2, and C is minus 3. A is 1, B is 2, C is minus 3. You put those in, b squared, that's 2 squared, minus 4ac divided by 2a. And you use a plus, you get one answer. You use a minus, you get another answer. So this here is, this is 12 plus 12. So this is 16. Square root of 16 is 4. So it's going to be minus 2 plus 4 divided by 2, or minus 2 minus 4 divided by 2. So those quadratics always have two answers. So that's all for the quadratic formula. Okay, that's all for the basic algebra you're going to need to get started. But one thing that we will need to get started also is going to be graphing. So it's going into the second half of this class. Normally, if this was a physical class, we take a little break. We don't have to take a break. So this material is going to be related to the lab that we're going to be doing, which is going to be lots of graphing. So what do we do this? Let's take a little break, a 5-minute break. I can get a glass of water. And we'll come back here. And in 5 minutes, I'm going to spend probably another half hour on graphing. Okay. I have the slides up here, but I'm not. I'll be back in 5 minutes. This is too much. You put your mind through. So while we're waiting, does anybody have any questions they want to ask? These are some sample graphs about the economy, Obama versus Bush. And of course, a more relevant graph now would be the pandemic. For example, this is New Jersey, how the pandemic looked like, how many cases per, I think, 7 days they're looking average. There were back in April. And in New Jersey, we've been very lucky. We've got it down, and we're sort of keeping it down. Obviously, Florida is also doing that, but kind of late, much after us. So these are graphs of something called exponential growth. And exponential growth generally will look like this. This would be a perfect exponential growth, like population growing. Exponential growth means something doubles every given amount of time. And it also goes the other way, exponential decay. And so basically, the left side of the graph is approximately exponential growth, and the right side is approximately exponential decay. It's approximate because that's the way life is. Now, so we're going to make graphs also. But let's look at the very simplest graph. Let's say I drop a ball from a certain height, and it drops down, hits the ground, and comes back up. So the ball drops, hits the ground, and bounces back up to this point. And I'm going to collect data. I want to see if there's a relationship between the height dropped and the height of bounce for this particular ball. And of course, you say, well, of course there's a relationship. The higher you make this, the more it bounces, the higher it bounces. Right, true. But I want to know exactly what that relationship is. So I want an equation for it. So I made up some nice numbers that you actually don't have to do anything but look at the numbers. Say I drop it from 75, it bounces to 25, 60 to 20, 45 to 15, etc., etc. So what's the relationship between these two variables? These are called variables, height dropped versus height of bounce. Well, you can look at the data and you can notice something here. I noticed this is 3 times that. So I can say the relationship is height of bounce is 1/3 height of drop. But if you take real data, you're not going to get numbers that are like that nice. You can't just look at the numbers and say, oh, I know what it is. Here are some sample numbers of a real experiment. So what do? You make a graph. So in a graph, a couple of things. Number one, you have to label each axis. What are you going to put on each axis? Height bounce, height drop. Well, obviously you need a graph paper. Height of drop, you look at the numbers here, height drop, they go up to 60. So you make a scale so that you can get up to at least 60. So if I go by tens, I can get up to 60 and even more, even though I won't need this, but by tens, I can make 60. Height of bounce only goes up to 22, so you're not going to go by tens because you're going to squeeze the graph into tiny little space like this. You don't, like this, around here. You don't want to do that. All right, you want to use most of this graph paper. So you make a different scale for the height of bounce. Go by fives. 5, 10, 15, 20, 25, 30. Yeah, so 22 is your biggest number. So that means you will use this much of this graph, which is for our purposes here is okay. You want to use as much as possible. If you have a big graph paper, you can make a different scale. So first thing you're going to do, each of these is going to represent a point on this graph. So for example, well, let me go to the next slide. These are the points. So this is 60. That's the first set of data is right over here, 60 and 22. Then all the other ones also. Each one of these is a dot here. Now, these dots would tell you if there is a relationship. If the dots are scattered, there's no connection. But obviously, they're not scattered. They appear to be connected by a straight line. Okay. And that's good news. A straight line, especially if the line goes through the origin, it's very easy to find the connection between the two. They're connected by finding something called a slope. The slope, imagine yourself walking or moving from one place to another place. Two things happen to you. You go up, or your y changes, your y coordinates. It changes by this much. And your x changes by this much. This is delta x. So in our case, what does it change? What's the change in y? We go from 0 to 30. It changes by 30. This goes from 0 to 90. Don't forget, I chose this number, this position, and this position. I could have chosen any two positions. The numbers would have been different, but the slope should be the same. And this is past our data. We don't even have data up here, but that's okay. The slope would still be the same. Take the two points here as far away as possible. Otherwise, you're going to have to say you take this point and this point, you're going to have to approximate what delta y is. There's going to be a big error here. The slope is delta y divided by delta x, in this case, would be 1/3. And therefore, the connection between the two variables is equal to that y to mx. The y variable is equal to the slope times the x variable. So height of bounce equals 1/3 height of drop, same as before. Same as before. Now, if you wanted to find out, for example, we never dropped it from 40, okay? But you can, from the graph, you can figure out what would be the bounce if you did drop it from 40. No, you did drop it from 40, right? So we never dropped it from 55. 55, right over here. So 55, it would have been about 26. I'm sorry, 16. It would have been 16 from 55. This is called interpolation, finding the data between points. Extrapolation is finding the data past the last point. For example, we never dropped it from 100, did we? But again, you can go past the point here, and what would be 100 would be right over here. So height of bounce would be right over here, about 32. That's called extrapolation. Some real-world data. Let's say we have a bunch of circles. I'm going to give you some data. It's a little circle. The diameter is 2, and we're going to measure the circumference of each of these circles. We're putting a tape around. And I had nothing to do, so I actually did that. So 2, here's the data. This is the data. We'll make a graph of the data. All right, don't forget, when you make a graph, first you prepare a data table. This is the data table. Then you label the horizontal and vertical axes with the same headings used in the data table. In other words, D and C. I'm going to do it real quick here, but the next slide I have nice. Choose a scale. You're going to make up a scale. What are you going to call each box so that you can fit up to 20? Don't, go make the graph from here to here. Try to use as much of the graph paper as possible. Make a scale so you can get up to 20. This way you got to make different scales because you're going to get up to 50. Then graph or plot the numbers and draw whatever curve it signifies. So here it is. Here's the scale. I went by 1, 2, 3, 4, 5. Means each box is 1. This way I went 1, 2, 3, 4. Each 4 boxes is 10. All right. And that fits all the points here, up to 50, up to 20. Exactly. Plot the points. Here's the points plotted. One point seems to be off. These seem to indicate it's a straight line, but one point seems to be off. You know what we're going to do? We're going to ignore it. whatever fool made this measurement, whatever tape he used, he made a mistake. We're going to ignore this. These seem to be okay. They're not all on this line. Now we are going to do what? To find the slope, right? So we pick any 2 points. Here I am picking the points. I picked this point and that point. I chose the corner of the box. And I'm going to find delta y, delta x for these points. Here it is. This goes from 0 to 40. No, 40. From 12. From 12. Actually, this is not. This is from here. Well, that's delta y, and this is delta x over here. 13 minus 4. And it turns out to be 3.11. What's the connection between the two variables? Well, y equals mx, right? Y variable equals the slope times the x variable. Y variable is c. The slope is 3.11. The x variable is d. Does this equation look familiar? Yeah. Circumference equals pi times diameter. Pi being 3.14. Now you didn't get 3.14 exactly, but you were pretty close. There's a percent error. Percent error is calculated by finding the difference between the two numbers, what you're supposed to get, minus what you got, divided by what you were supposed to get, and basically multiplying by 100 to change this from decimal to percent. That's the percent error. Now let me just do the calculation here. 0.03 divided by 3.14 is equal to, that's a very small percent. Almost less than 1% error in this case. So I'm not going to do this, but you could, any line you can find the slope. The line, be careful, the line does not, if the line does not go to the origin, you can't just use the coordinates. You have to look what the length of this is by reading 70 minus 30, and what the length of this is, 40 minus 0. Okay, so what's the slope of that line? Well, 70 minus, in this case minus 20, I'm sorry, is 50. And that's delta y. This distance is delta y. Delta x is this distance. And that's 50. Slope is 1, believe it or not. Okay, so I'm going to skip down to something that's really more closely related to our lab, and that is finding we're coming back to the same circles we had before, but this time instead of finding the circumference, we want to find the area, and we're going to find the area without using any formulas. We're basically counting the boxes that fill up this, counting the boxes that fill up that, and get an approximate area by counting the number of boxes that fill each of these circles. Again, I had nothing to do, so I counted the boxes. Here they are. This big circle had 1,270 boxes in there. That's the area. It's 20 centimeters diameter, or the radius is 10 centimeters. Let's make a graph. Okay. Now, when you make a graph, here it is. You don't always, and this is the kind of, you count actually, for these circles, like this is the area I used, 250. This is the data I used. You make a graph, area that way and radius this way of this data, and you get that. It's not a straight line this time. Oh, look at that. It's not, it appears to be like one of these curves that, oops, it's hard for me to make the curve, but this should be a smooth curve here. It goes up like that. And that tells you something. If a curve goes like that and not a straight line, or it goes like that, curves down away from the straight line, that tells you something. It tells you this. That, and I took the slide that had right here, that the connection between the two variables that you're graphing is that y, whatever you're graphing in the y, is equal to some number, some constant, times x raised to some power. And if it curves away like this, then that power is bigger than 1. If it's equal to 1, it's a straight line. That means the power is equal to 1. And if it curves down, it means the power is less than 1. And don't ignore the other graph. That's what happens here. Okay? And that's going to happen in a lot of places. You can see over here on this graph. But over here, we can see that the what we're going to do is we're going to guess that the connection between the two is that the area is proportional to the square of the radius. Don't forget, y is equal to k x to the n, and we're just saying that n is equal to 2. I don't know if it's true, but I take a guess. If it's true, if my guess is true, that if I were to make a graph of y, in this case, this area, versus r, but r squared, I should get a straight line, and that line should have a slope of 2. That line should be a straight line, right? A slope of 2. So there you go. There you have the graph of this area versus r squared. It is a straight line. And it probably doesn't go quite through the origin, goes a little above the origin, but the slope of this is that power. What's the slope of this? Well, 80, say 260 minus 80 is 180, and this is delta y is 90 minus 30 is 60. So the slope, for some reason, is not what it's supposed to be, because it's 60, that's 3. Oh, yeah, okay. That is right, it's 3. And the fact that it's a straight line tells you that it's the relationship is equal to between A and R, that they're proportional to another, because you use the square over here. And the slope is, in fact, this number here, right? Going back to this slide, we want to find out what this number is, what's the constant. The fact that it's a straight line tells you that n is equal to 1, n is equal to 2, I'm sorry, because we squared it. And the slope tells you what this number is. And what is this slope? What should the slope be? Pi again. Area equals pi r squared, right? And we took a guess that a 2, by squaring this, by squaring all of these radii, would give us a straight line. We didn't know that. Obviously, it was an intelligent guess. So we're going to skip over to the lab that's coming up. Now, this is how we're going to work this lab. There's no lab this week because there was no school this week at Monday. labs on Monday. There's going to be no lab next week, but there will be. But the lab will be on your own. I will make a video on Monday, a little more sort of repeating not repeating what I did here, but repeating what I'm going to say right now. How do you do the lab? I'll make a video there to sort of refresh everybody's mind. And you'll have all week to do it. Okay? So let me just show you what you're going to do. Okay, let me go. So I have somewhere here a picture. Why can't I find it? Yeah, I'm going to sort of outline what we're going to do, and I'm going to put more detail in the video. So first of all, we're going to look at a simulation of, it looks like this. Not that. It looks like this. We have a pendulum, okay, and if we displace the pendulum like this, a certain number of degrees, it swings back and forth. Okay. The time for one swing is called the period. Normally, you find the time for one swing. There is a stopwatch here. I'm going to stop this. I'm going to bring this up, let's say to 20 degrees, and I'm going to time it for 10 oscillations. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, I went a little over. It was 17 seconds. All right, so 17 seconds was for 10 oscillations. I'm going to make some hypotheses. Will changing the weight change the period? Changing the weight. And you can change the weight right over here. Will changing the length change the period? Will changing the angle from a small angle, let's say 10 degrees, to a big angle, 20 degrees, would that change the period? Which of those matters? And for the first part, I'm going to ask you to do just this. Now, this is what you're going to do. You are going to go to where it says